is like an integral part. So the second one is definitely acidic salt. So you have to go for like that. And it was what I got. It's just like no, it's basic salt, right? Because it would be like H plus with aniline with O. Yeah. Okay, so no, it's not. It's yeah. So then you just do more salt. Yeah. Base and a weak acid reaction. So don't you just have to compare everything stuff? I don't think actually do anything. Just compare like their values and just do a reaction. You find like some
Alright, and come back to me for the first three. I'm going to kind of see where we are, and then I'm going to hit the review, and then we'll do the next three, okay? So for the first one, this is called aniline. It's just a weak, well, it's a substance, which if you did not write that down just right here, anytime you have an NH2, it's like an amine group, and the amine group acts basic. So NH2 can act basic, meaning it can accept a H to become what? Blah, blah, blah. What's on the end of once it's accepted an H? NH3 what? Plus, right? Do not forget your ion charges, because when I look for reactions, then you have the correct charges. So speaking of that one, this is a more common one. Like aniline has like a benzene group on it, which is that C6 kind of like hexagon. But methylamine is a more common one, or ethylamine. So you hear the amine group on the end. So amine means NH2. NH2 is the weak base. Write out just someplace on your paper the conjugate acid of this guy. And for my viewers at home, methylamine, CH3, NH2. What's that conjugate, Darcy? Excuse me? So this is a base. This is a weak base. Bases do what with acids, or do what in water? Okay, so it's going to make a conjugate acid. So you have to make this more acidic. Okay, back to the definitions. Bronsted-Lowry bases. What do they do?
They accept H.
Okay, make it accept an H.
Oh, H3
plus. Okay, so this is H2, H3 plus, that's it. Please don't get too crafty. Don't try to shove the H over here. If this is going to be like a CH3 structure and so forth, so you can't add another H there because it's already saturated with H's. So just add it on the end and then have your plus charge, because that's like protons are being exchanged, so that's how we're going to denote that. So then this is a what, guys? Just classify it. This is a weak base. How will you solve for pH? Find using its Kb, which would be provided for you. You're not going to find it anywhere. Like I will provide that for you. You'll use the Kb instead of icebox. You'll solve for X, which would be actually solving for what? Ions? Hydroxide, because a weak base should be making hydroxides in water. Find your pH from that. Moving on. Next one, identify the type. It's a salt. And actually, you can decide on where it lies on the pH scale right now. You know, it's going to be basic. Why? Okay, so sodium comes from a strong base. Chlorite comes from a weak acid. You know it's going to yield the basic side once we actually find the pH. So that's just a thought, or some food for thought. We'll keep our eye on. Which ion is important? Okay, so the chlorite, we're going to add that to water and make what? Chlorous acid. Hydroxide. I'm squeezing what's in here. Okay, so once we make hydroxide, we know that we're going to be solving for hydroxide. So we're going to have to find what with this though. Not quite. Don't jump too far. So this is going to be us setting up a what? ice, but this guy's behaving as a base. But this ion is not truly a base. There's no published Kb for it. So use Kw and Ka. What Ka? The one for who here? Fluorous acid, right? So you'll find Kb of Ka for, I'll write it the same way I wrote it earlier. Okay, so we'll find the Kb from the Ka of this weak acid that we have provided. This will be given to you in the problem someplace. Once you find the Kb, you set up an ice and you solve for hydroxide. Yes?
So it'll give you Kw and Ka and you just divide them to get Kb?
You don't have to know Kw, I'll give it to you.
Okay.
So but what I'll do is, like on your quiz, you'll have a list of all the things you're solving for, and you'll have a list of Kas or Kbs that would be published for a given base or a given acid. Yes?
What's the thing that you do if like water's on one side and you do like the other?
That's only if you're looking at an overall reaction, you're trying to decide how, like what that reaction is describing. It's describing the ion acting as an acid or base compared to, I gave you guys a diprotic one, so I had like a lot of moving pieces. You won't have to do it like this. Like you'll just simply decide if it's an acid, base, or salt, and then go with solving for pH. Okay. Okay, so 3, decide, type it first. Okay, it is a salt, and then what kind of salt? It's a weak acid, weak base, right? So I have not shown you how to actually solve the pH for those, but you can solve for like the range, like if it's an acidic or a basic salt, but you have to take a couple steps. So what would you do? Write the what? Find the Ka and Kb of those ions, not the ones I published for you, because the Kas and Kbs I published for you are for the true acid and the true base. So ammonium would be behaving how? Come on, guys, there's an H plus here. It's got an extra H plus. It doesn't want any more, so decide. It's a donor, right? So if you have to like think about, okay, like who would I be able to donate? You've never seen an NH5 2 plus, ever. So you're definitely going to have to donate. So it's going to make hydronium and what? NH3, ammonia. So it's behaving how? As an acid. So you must find the Ka from the Kb of who? NH3, which is the base that we truly have a Kb for. And then the other half of this would be cyanide, behaving how? As a base, because it has a lack of an H plus, so that's the negative charge. It's going to attract an H plus, making what? Hydroxide and cyanic acid, and then you say it's behaving how again? As a base, so you found the Kb from Ka of cyanic acid, B acid. So just make sure you're using the right Kas. So Emily, once I get to these, this Ka and this Kb, what do I do? That's it, right? Kb is bigger, it's basic. Essentially for a weak salt, it's going to actually form a buffer. It's like our next part of this unit. So later on we will determine how to actually do this, but in essence, if you're making more of these products, that means your Ka is large, because large Kas mean products are favored. So if you make more of those products than of these products, you have more H plus in solution, which is going to yield it to be more acidic, and then vice versa for the other. So that's what we compare Ks. All right, decide how you would solve the next 4 through 7.
Before you getting back on the whole reaction of nitric acid with
Yes.
So you just write down the reaction, and then find out what we need.
It'll make it salt and water.
What is it? Excess and excess.
Once you figure that out and you're using like moles, then you'll probably make the moles like salt.
Yes.
And then from there, you'll just normal process. Okay, so
Yeah, we find the holes.
Water and
See, they come out really fine. Of the equation. You would use that to find the pH. That's my
I was thinking about maybe do activate reaction and then increase the salt and with this because they're both strong, so it's gonna 100% react on both of them. So from the salt, you can do the normal process.
Not if one is an excess. Not if one of those is an excess. Salts are nothing compared to like full on.
carbonic acid.
Oh, H2CO2. So that's
HCO2 carbonic acid.
so that's not a strong acid, so it's a weak acid. Do you have to do it's like H2CO2, so you have to do the weak acid reaction with water. You know, it's an acid. It's just like
All right, Ian, come back to me. I hear some of us are farther than others, but hopefully we can clarify as we go. Raise your hand if you're confident on 4 how you'd approach this. Cassie.
When you first go to millimoles of pH,
Okay.
and then you can set up your VDA, and you have to find which one's the LR.
Okay, so pause for a second. The main point about throwing out this one was that you know, the video you guys watched over like midterm break, that video showed you a true reaction. Like it wasn't a mixture of 2 acids, it wasn't a mixture of 2 bases. This was a strong acid, strong base reaction. Anytime we have like true reactions, we don't make ice cables. Like a true reaction that goes to completion, something's gonna run out, right? So that's what we're talking about LR. One of them is gonna be in excess. That's where we have to use BDA. And in BDA, we don't use molarity. We use what? Moles or millimoles, because you know I don't want to convert. So you're right. We'd have nitric acid and calcium hydroxide. We'd react it to make salt and water. I actually don't care what the salt is here, because anytime you have a salt in water, it's going to be negligible in terms of like how much it contributes to pH compared to one of these strong things that are left over in excess. So once you find millimoles of both, I'm not solving this problem. We're just going through the process. Once you find millimoles of both, how do you determine LR? Quickly. Divide by its coefficient. Don't write that number down because it's not really the number you're using, but you do it in your head and say, okay, I'm going to put them on the same playing field by dividing by their coefficients. Whoever's lower runs out first. So in that case, you'll subtract one of these. Let's just say, I have to balance this. I'm going to say the acid is the LR. So this one's gone at the end. There's none. If you have excess of the base left over, how would I solve for pH in here? Cassie?
You take the excess and you divide by the total volume.
Good. So this will be in millimoles of calcium hydroxide. And you divide it by the volume milliliters, volume total, because milli and milli will cancel each other out to leave you moles per liter. So that'll be molarity of calcium hydroxide. Keep going.
And then that's your calcium hydroxide, so that's the base excess and arrangement concentration, but because there's a 2, you have to multiply the molarity by 2.
So this is calcium hydroxide molarity, but calcium hydroxide delivers 2 hydroxides for every one of itself. So yeah, you're going to multiply the concentration of that by 2 to get the concentration of hydroxide, and then pH would be 14 minus negative log of OH. That one's a long one. That's not like a simple ice box. Questions here? You good? Okay. So you'd actually have to run through the whole VDA. For the next one, type it. What do you guys identify first? It's a weak acid. Okay? If you have a weak acid, I would have given you what? A Ka. So the Ka value would be helpful there. And then once you know the Ka, you know it's a weak acid. What are you setting up? Ice. And then you're solving for X, which would be H plus, right? It would be the hydronium, and then you'd solve for pH from there. But yes, you take this and write the reaction out first, so you donate the H in the front to water. Next one, identify first. Okay, what kind of salt? A what? An acidic salt, good. Some of you guys said neutral. Is magnesium hydroxide strong? No, there's only 3 strong bases that are dibasic, so calcium hydroxide, barium, and strontium hydroxide. So chloride is coming from HCl, so that is our strong acid, so this should be acidic. Which of these ions would we care about? Magnesium. So this is a weird one to actually write out. I actually wouldn't give this one to you because it's a weirdo. So we'd have to add this to water and then make hydronium, or make hydroniums. So we make magnesium hydroxide. And H plus left over, so we'd have to solve for a K. Yeah.
It says that magnesium hydroxide is a strong base.
It's not a strong base. That I can't really remember where I got that list from. It was just so inclusive. I was like, this is the one. So I printed it for you guys, but it's not actually strong. It's stronger than a lot of bases, but it's not technically, of the 8 strong bases, it's not one of them. Just like on there it says chloric acid, right? Chloric acid. It's stronger than a lot of acids, but it's not as strong as those 6 strong acids we memorized. So I kind of follow the AP schedule on that one, not random things I find online. Okay, so let's just do 2 more. Or start with 7 and just identify first. It's a what? It's an amide, or amine, okay? And weak base. Okay, so if you see an H2 on the backside, there's a weak base. I would have to give you what? KB. This is ethylamine, F with 2 carbons. So ethylamine has a KB associated with it, and then you set up a what? Ice, and then we solve for X from the ice. It would be equal to the concentration of OH, because you would be producing OHs in solution. Okay. Let me see if I actually want to do more of these. Because I feel like I've killed you with this. And like, if you're feeling good about this, you just need to keep looking over how to do them. Because once you get into the process of iceboxing, you're usually fine. How about 10? How would you approach 10? So what is this a mixture of? 2 strong bases. So what do you need to collect together? All the millimoles of both. Okay. But what's so weird about this one? It makes 2 hydroxides. So you'll get millimoles of calcium hydroxide and millimoles of sodium hydroxide. For the millimoles of calcium hydroxide, you double 2 times the millimoles of calcium hydroxide because of the basic nature, plus the millimoles of sodium hydroxide. And then once you get this, what do? Divide by what? Volume total in milliliters. And then that's going to give you what? I heard concentration of hydroxide. And then you can find pH from there. Okay. Alright, so just you'll have a mixture of things, but the most important thing for us to know is identifying the salt. I think that's still the challenging one, and then determining how to go from there. Yeah.
I think yesterday when you told me that we won't have to that end. Is that when you had?
I was looking for a BDA. Okay, so today, let me skip that for a second. Today we're doing a diprotic dry lab, and it's in your packet. We'll get there in a second. And then talking about just a couple more, like differentiating between different types of equilibrium problems. So, but I need to finish up a couple like random things I haven't finished from notes yet. So I'm hoping for 10 minutes of your undivided attention, and I'm gonna go. I gotta fly back a couple of slides because there were random things I skipped that I felt were important. At one point in time in my life, I felt it was important to talk to you about it, so I think it's still important. Okay. This was the one question that dealt with percent ionization on your NMS side. So I didn't want to neglect showing you how to do this if you still need some help with it. So we had the lactic acid, 0.1 molar aqueous solution of lactic acid, which is 30.7% dissociated. That percent dissociation is giving us information about X. So that percent dissociation is technically related to X. And that's the relationship, because that's like our 5% rule. So the 5% rule is always taking X divided by the original acid, or the original concentration times 100. So 3.7% is equal to this setup. You can solve for X, which in this case coming from an acid would be the H+, would be 3.7 times 10 to the negative third molarity, or molar. So once you have X from that percent dissociation, you're probably okay with seeing the finish line here with how to use the X in the icebox. But knowing your X now and setting up, you can see, like, you see how I shortcut my icebox? I don't do I, C, E, just kind of throw it all in the E part together. So I'm making X and X amounts of both products, singular reactant minus X squared over the initial, and then because we know X, and normally we would neglect it, but because we know it, we're actually plugging it in and then solving for the Ka value for that lactic acid. So that's old news. Sorry, it's been a while since I've had you guys do that one, but that's a good reminder for us if we need it. Just give me a thumbs up when you're good with that one. Now, often we could just start with the dissociated percentage, so that's just a different way of approaching the problem. Okay, other random things. Hold on. Some things are actually I need to go review. So I just wanted to show you, this is our diprotic, like from the diprotic day. There were a couple of acids that we know are di or polyprotic overall. So if you look at sulfuric acid, do you see where the acidic hydrogens are? You see they're red up here? So just note, it's not like embedded inside of the structure, it's on the outside of the structure. And like oxalic acid is on the outside of the structure, sulfuric acid is on the outside of the structure. Why would it have to be on the outside of the structure? So who's pulling it? Right, water's attracting it. So water's not going to attract it from the inside of the structure and just destroy the entire structure. It's just a very minor kind of removal process. Even citric acid, H's are on the outside. You can see this is a what kind of acid? Say again? Sorry, of the polys, mono, di, triprotic, so you see the H3, and then there's 3 H's here, and then there's 3 Ka values. So all those correlate. And then even down to carbonic, which is more familiar to us, those are 2 acidic hydrogens. So not every hydrogen is acidic. Do you know what I mean by that? So it means it does not pop off to produce H+ in solution. So some hydrogens, like this hydrogen, are those acidic? No, because they don't have the ability to make any solution acidic. And then we'll talk about this a lot more today, but you'll notice with anytime you have a diprotic acid, we mentioned like the single deprotonation step at a time, so it delivers the first H and the second H and the third H. And so when we do a titration with these, look how funky this curve looks. You can see like the single H+ delivery. So in the first equivalence point, you're dropping off the first H, and then the second equivalence point, that's when you're neutralizing or taking away the second H. In this case, this is diprotic. But this is actually what our activity is focused on today. So just notice they look a little different than our normal titration curves. You get that point? Looks different? That's really it. And then I didn't have you do a problem set. Do you guys want to go back and do that? You okay? Okay. I didn't have you do it, because we practiced it in class. Okay, so we went over that yesterday. I've already done that with you guys. The Lewis acid part is the part that I've not really discussed at all outside of like the definition of Lewis acids. Lewis acids doesn't really, that definition does not focus on H+. What does it focus on? Electrons, just like Lewis dot structures focus on electrons. So I'm going to show you from this reaction and this reaction. The one I've highlighted is one you absolutely need to write down, because it's one, it shows up on the AP exam kind of often. So looking at this equation first, Lewis bases are donors of electron pairs. And so you can actually see that in this. Ooh, does anybody know the name of this? We have an O in the middle. Something on ether side.
Oh.
It's a what? What is this overall? That's not going to be F. It's going to be 2 singular carbons. Dimethyl ether. Yeah, so dimethyl ether. Just reminders, okay? So that little lone pair right there is going to get shared. The entire lone pair gets shared. But what's weird is it doesn't actually remove the lone pairs from itself. It actually says, okay, you're going to come and bond with me. So this lone pair is going to make HCl kind of bond with itself. So notice here, the original structure is here, CH3, CH3, and O, and then the H is getting sucked into the lone pair and getting bonded to the O now. And so that bond right there is because the Lewis base shared an electron pair. So then the HCl was acting as Lewis acid because it accepted the lone pair. So it behaves similarly in acid and base behavior. It's just we're not focusing on H plus transfer all the time. We're focusing on lone pair kind of sharing or accepting. Because now this one contained a true acid, like HCl. We know that's definitely a hydrochloric acid. But down here, this next one, which is the one you certainly need to write out, it doesn't have like a true acid, which is why we're speaking of this third type of definition, which is kind of talks about that excluded behavior, which is the lone pair transfer. So in this case, why is ammonia the Lewis base? It's giving away its lone pair. So it's not just a singular electron, it has to be considered the lone pair. And it doesn't just truly give it, like donate it fully, it actually forces a sharing relationship, which is what electrons do. They like to be shared like in a covalent situation. So that lone pair goes over here to bromine or to boron, and it forces it to be shared between the lone pair to be shared between the nitrogen and the boron. And so we actually make something called a coordination bond. There's like 2 or 3 names. Coordinate covalent bond. It's just a covalent bond. Like you can see, it's just shared, but it formed a certain way. It formed not by 2 electrons giving 2 different electrons to a singular covalent bond. It forms from a single atom giving both electrons to the single covalent bond. Normally, boron would put one in and nitrogen would put one in, but in this case, nitrogen put both of them in, so we call it a coordinate covalent, not just a covalent. That's very minor for you to know, but just be comfortable with seeing this kind of flow. We okay with that? So that's just a random Lewis definition. You really don't see it too frequently, but I think when I not tell you that. Thumbs up when we're good to move. Okay. So pull out your packet, because I think I have one more thing to show you. And then I'll tell you how we're going to break this down. Right. Am I good to get past this? Feeling you good? Alright, so basically you guys are going to find this diprotic acid dry lab, and I'm calling it a dry lab because we're not literally doing the titration, but it's still a practice of lab skills, especially interpreting a titration curve. So you will put it in your lab notebook because AP can, like when I submit my syllabus, I tell them what labs are doing their wet lab and what labs are doing their dry lab, so I ask them to make sure that you're held accountable for this in your lab situation, like in your college. So you guys have data, and you have like a little pre-lab reading. The pre-lab reading walks you through just a little bit more information about diprotics and how it would not just be diprotic dissociating in water, but a diprotic reacting with the base, like a true reaction here. It's not actually like equilibrium when you go over there. So, okay, on here there are double hitters, but they're more of a completion reaction. And to make this easier, I printed out the diprotic acid, or the diprotic titration for you. And I have the Excel file on my website. If you like, I can't quite estimate, is that a 5 or 4 or 5.5, I mean, whatever it may be. So you'll annotate on here wherever you want to. Have like handfuls. You guys just make sure everybody gets one. I give a lot to that group, so go from them. So after you read and you get through starting some of the questions, you'll start writing those questions and just the answers in your lab notebook. and you can cut and paste things in your lab notebook as needed. So I'm going to give you guys about 30 minutes max to do that. Okay? If you want to work at a lab station, you can work with one other person, just because as more people get together, you get more and more off task. I know you will. Okay? So extras I'll take. So if you can somehow squeeze it in your lab notebook, that is your goal. And for those of you who want the actual Excel file, so you can hover over a point and you can actually see the exact point values, I'll show you where that is on my website. It'll be under Unit 8, Acid-Base pH applications. And it says Diprotic acid dry lab graph. That's the Excel file if this is just not your jam. Okay? Okay.
How you find this?
This is okay, so just keep talking to me.
Just polyprotic.
You will actually use one of the either a Ka or K1 or K2.
Make it as close. Make it as close.
Right, so HCO3 is a bicarbonate, right? Bicarbonate is amphoteric because it has an H it can donate, but it also can accept an H plus back. So what I told you guys was write out, this is like a pre-lab, write out whichever style reaction you want and make it act as an acid or make it act as a base. Use the right K for that and find the pH, and you're going to compare that to the pH that was achieved. So obviously here you can see it's acting how? Basic. So if you now that you know that, you can actually write it out acting as a base.
Okay, and when you have polyprotic acid and you have 2 Kas and stuff, do you add to what you do with them? Do you just list them?
You don't list them though. You're gonna, since you have that, and so let's just say we're gonna make it act as a base, right? You have, how would I make this act as a base? And, right. So note the 2 ions that are here that play into Ka or K1 or K2 are this guy and this guy, right? You see those are like basically the same. Oh, sorry. The substances that are here. To give you information, am I talking about K1 or K2? I'm telling you, you have this and this. So with these two, the appropriate to call K1 or K2. Is the first deprotonation? Okay, yes, KB from
KB2.
Yep. No. See how this is a combination of just the first deprotonation because it's H2 and H. The second deprotonation, which would be the 2 version, would be a combination of this and this because it's the second deprot. This is the first decrypt because you've only overall exchanged 1 H plus. Okay. This shows the secondary one. So this would be KB1 from KA. 1 because see it's still the first version of carbonic acid in the reaction. The first version, which is not deprotonated, and then the second version, which is only one step, so 1 deprotonation.
So that would be K2 as well?
Yeah. This would be KB2 from KA2 if you chose to do that salt reaction, but you said you want to make it act as a base, so we went with that one.
So the questions are specifically asking for things like polyprotic. How would you list the answers if it was asking for the K?
If it was asking for the Ka of a polyprotic,
Would you say K1 or K2?
you probably have to write out the similar like deprotonation steps, and so like the first step would be K1 and the second step of deprotonation would be K2. So yeah, you just do it up. Unless for some reason it's like it's the overall Ka, which would be K1 plus K2. Has it done? You should do it for
Is there a video from us going over the homework from yesterday?
From yesterday? There's a video up from yesterday. And the homework that we went over in class is up. Yeah.
Okay. And secondly, the importance of like Six. Okay, so we have like a salt and like part of it is a strong acid, the other part is a weak base.
It's coming. I'm not going to say it is a strong acid or is from. It's coming from.
Okay, so that's where they're coming from. So the strong base, or sorry, the strong acid, that would be from the products of the first reaction. Or
What do you mean the first reaction?
like if it's like Cl minus, we have like a chlorine ion, and we would call it a strong acid because it forms into HCl.
We would say it's the conjugate base of a strong acid.
Okay.
Yes. And so if we were to write the reaction out, reaction with water, like salt hydrolysis, chloride reacts with water, it would reform HCl, right? And we're like, no, HCl does not stay as its combined form. It's going to reionize for the reverse reaction. So that first half reaction, I'll call it no reaction, which is why that ion is irrelevant for determining pH.
And secondly, we're like guessing what the pH is going to be, like the overall pH for the final answer. That is like we was writing like acidic salt. That's what that would be. So it wouldn't be either of the individual reactions that we create from the salt.
Okay, so I think that question was phrased incorrectly.
Yeah,
So
I'm not
we are.
explaining this.
So basically, when you're looking at your two ions, and you say to yourself, okay, NH4Cl, okay, you have, if you have NH4Cl, all you're doing to yourself is to set yourself up for success. Is you're saying this came from something, NH3, right? So this came from NH3, which is a weak base. So this is the strong conjugate acid that's going to be very important for the half reactions you're going to write in a second. This came from HCl, which is a strong acid. So comparatively, parents, those two parents, control the pH of the salt. So these two parents, weak base and strong acid, is going to yield. The acid's going to win, so it's going to yield an acidic salt. And that's just when the salt dissolves in water, it's going to make it more acidic pH. But then your job is, that's just like predicting, that's honors and stuff we do. Then for our purposes, is we take one of the ions that's going to make acid and make H3O+. This is the one that makes H3O+ in the solution. This will not, this will yield in the reaction. So that's right. This gives us hydronium, because this H+ is acidinated, and ammonia. And then we go through and do an icebox with the K wet for this one.
K.
So this is actually an acid, right? We have to get the Ka from the Kb of ammonia, because you will not be given a Ka for ammonium. It's not a true acid. It's just behaving as such.
Okay. So we get K8 from the Kb through the
Correct, by using Kb.
Okay.
Right, and start your jump part.
Thank you.
My graph is yours. Y'all up on it? Personal.
If you're good to go, you keep on going. I'm going to show some folks who are struggling on the species part how to approach this question. So if that's you, just eyes up so I don't have to repeat this. Before the reaction begins, all you have is H2X. And I know you guys know the compound now, but I'm plugging it in X's just so I can write this easier up here. Before the reaction begins, it's all you have. As you continue to react, you're adding it to sodium hydroxide. And sodium hydroxide. And at this point, at your equivalence point, your first equivalence point, the only thing you have present, because all of the H2X is reacted, and all the sodium hydroxide has been consumed that has been added at this point. The only thing left are the products of this first reaction, which should be what and what? Double replacement, come on, water and sodium, Na, keep going. Oh, so I'm going to put ions in just a second. Just give me the products, literally the products in the first reaction on your pre-lab reading. H, X. Okay, it's the first deprotonation step. Basically, you have an H still there. So these are not the ions that are present truly. So the ions, water doesn't count because it ionizes such a little amount. You'll have sodium ion and HX minus ion. So this is really the one that matters, is the thought of like how does this deprotonation step occur. So on the secondary kind of side of things, this green line is showing you what new reactants. Because I'm starting to add more sodium hydroxide, right? So I know sodium hydroxide is being added, but what is it being added to? Say again? Now I could say sodium HX, but the sodium is just going to be spectating, so it's hanging. So who's really the guy reacting with this base? The base, I mean the acid, right? Which is going to be who? Loud and proud, people. H, X, minus. Okay, so this is the first conjugate base that is made. So conjugate base that is made reacts with the rest of the sodium hydroxide that's being added. And then at this equivalence point, what are the products? Okay, I heard X, what? Not just minus, because it's already X2 minus, and some water and some sodium ions. Those are all spectators, but still, you truly make, let me actually write that as it's listed on your paper. You make a double replacement reaction happen. So sodium gets with X2 minus, so Na2X, and water. But as we've stated before, water is not ionizing to an appreciable amount. Don't care. And sodium is going to ionize right off of that because it's a soluble salt. So the ion that is relevant is the fully deprotonated ion that's coming from H2X. Now you guys have your own compounds, so you'll fill those in. So essentially the first half reaction goes to completion for the first deprotonation. The second half, I say half reaction, first equivalence point goes to full completion for the first deprotonation. Second equivalence goes to full deprotonation of the second H+. Okay, so keep working for a couple more minutes on where you are. All right, back up here in 5, 4, 3, come on. 2, 1, all right. Ladies and gentlemen, back to me. I gave you about 45 minutes, so I need the last 15 kind of just to recap 2 things, and then I'm going to skip 1 activity because I think I can do it tomorrow. So on the question 12 and 13, you're starting to approach this new idea. So basically, when you're looking at a titration curve, you should be able to see past the curve. You should be able to read between the lines and see all this information now that's going to be eventually more relevant to us than it is today. So who read about the half equivalence point? That was question 12. Okay, not everybody quite got there, it looks like. So I'll quickly explain this in the minimalistic terms. So here's your equivalence point 1. Half equivalence point 1 is about here. And I say about, but I had values, I think you guys got 10.5 milliliters-ish as your first equivalence point. So halfway back would be what, 5.75? Yeah, half of 10.5. So you could get an exact value, so don't get like too estimated. Okay, so you can go back and find your half equivalence point volume, and it told you here at the half equivalence point, it kind of worked through the steps. It was like H plus is equal to K1, and then negative log of H plus is equal to negative log of Ka1. But to us, that ends up meaning pH is equal to pKa. So you can actually look at the pH on the curve. There's no guessing here. It's just plop back over to the y-axis. And that's your pH at the half equivalence point. And since you know your pH at your half equivalence point, you already know the pKa1 of said diprotic acid. So how would I backtrack to Ka1 from this data? 10 to the negative pKa, but we don't really know the K, right? But that's the same as saying 10 to the negative pH. And that would then give us data for pKa1, and then, I'm sorry, Ka1, and you could do the same for the second equivalence point, half equivalence point. Who's picking up what I'm putting down? Shake your head, thumbs up or something. Okay. I can explain more, but this is our first introduction to this, and we'll be utilizing this more this week. Okay. So the activity I thought was pretty good. We're going to skip for now. Open up your multiple choice practice, which is maybe 2 pages back, page back, okay? 1 through 45. You see that, right? Yeah? Okay. You're going to do half. You have about 10 minutes right now. Let's say a minute a question. Okay? I would like for you to get to question 25 tonight. So notice homework is half of multiple choice questions 1 through 45. You can bounce around, like you don't have to go in order. No problems there. And then reading Buffers Make Easy, which is our next topic for tomorrow. Okay, the Buffers Make Easy on our website. So right now, let's go from multiple choice to the last will be taken from after this. Who knows when? Right now, I don't know when. Okay. So you will finish your lab eventually if you've not, but right now I want you to work on multiple choice. We'll check in tomorrow.